Alright, first, before we actually do anything, we're adding nucleophiles to the carbonyl. So we're going to have a carbonyl, whether it's an aldehyde or a ketone, makes really no difference. But what happens is that the carbon of the carbonyl is partial positive. So it attracts nucleophiles. And when the nucleophile attacks, of course, you cannot have a 5-bonded carbon. So you need to break the double bond. And when you break a bond, you give the electrons to the most electronegative element. In this case, it's going to be the oxygen at the top. And you're going to now get a nucleophile attached to a tetrahedral carbon, and at the very top I have an oxygen that right now it's negative. This intermediate right here is the intermediate that we arrive at anytime we attack any carbonyl. So we're going to call it the tetrahedral intermediate. And when you get a tetrahedral intermediate, you check to see if you have good leaving groups. And this one doesn't happen to have any good leaving groups. Carbons, these are 2 CH3s right here, are going to be bad leaving groups. And the nucleophile that we just added, we're going to assume that it's also a bad leaving group. So since you don't have any bad leaving groups in solution, then the oxygen is going to pick up a proton from water or from maybe hydronium if you add a little bit of acid. So it picks up a proton, and we end up with an alcohol. So that's what we're going to see in these reactions when we attack the carbonyl of the ketones and the aldehydes. The first reaction we're going to do is a reduction with lithium aluminum hydride. And lithium aluminum hydride has 4 hydrides, and it's a very strong reducing agent. When you actually use lithium aluminum hydride, you have to keep water out of it. So the first step, you just add the lithium aluminum hydride in an ether solvent. And then at the very end of the reaction, you're going to do what I like to call the quenching, people like to call workup. But we're going to be adding water. And that's where the hydrogen on the oxygen is going to come from. So the hydride is going to be a hydrogen that has 2 electrons, and a simplified mechanism, of course, would be a hydride attacking the carbonyl, forming the tetrahedral intermediate. And if you form the tetrahedral intermediate in this particular case, you would have 2 carbons, or maybe a carbon and a hydrogen, and we just added the hydride. This is the hydride from the lithium aluminum hydride. And then nothing can leave, so the next step would be when we add the water at the very end, the oxygen picks up a proton from the water. So this hydrogen right here on the oxygen came from the water. This hydrogen came from the lithium aluminum hydride. Now this is a very simplified mechanism that doesn't take into account what the aluminum or the lithium are doing. But we also have a second hydride reagent, not as strong as lithium aluminum hydride, but quite useful nonetheless. It's sodium borohydride. We have seen it before in 3331, but now it's a much easier reducing agent to use. I don't need to have 2 different steps, and I don't need to have syringes for this reaction. Sodium borohydride can be used in an alcohol. And we see exactly the same thing. The hydride is going to be attached to the carbon, and this hydrogen right here came from the alcohol. So whatever alcohol you're using, it's gonna provide the hydrogen that goes on the oxygen. So we have 2 reducing agents: lithium aluminum hydride, incredibly strong reducing agent. Sodium borohydride is only good for ketones and aldehydes. So in that sense, it's a selective reducing agent. I have some examples right here just to make sure that we understand that lithium aluminum hydride and sodium borohydride react with carbonyls. So I have a double bond right here on the left. I am not going to be touching the double bond, it's going to remain in place. Lithium aluminum hydride can only reduce the ketone. This is a ketone, so I reduce a ketone to a secondary alcohol. This is another ketone. I'm using sodium borohydride. Notice that I still have an alcohol. This one is ethanol, but all I'm going to be doing is reducing the carbonyl. I'm not going to touch anything else in the molecule. The one at the bottom is an aldehyde. And notice that I have an alcohol on the left. Lithium aluminum hydride can only reduce the carbonyl. So it will take that aldehyde to the primary alcohol. So aldehydes are reduced to primary alcohols. Ketones are reduced to secondary alcohols, and we have two examples of that. Alright, this is one of my favorite reactions. It's the addition of a Grignard or an organolithium, if you have it, to a carbonyl. And the Grignard is a carbon that's actually negatively charged, and it's basically a salt of magnesium. So I have two negative charges and I have my magnesium in the middle between them. But what's important again is that the carbon that's attached to the magnesium, that's a nucleophilic carbon. It has a negative charge, so it will attack the carbonyl. It will form a tetrahedral intermediate, and this tetrahedral intermediate actually shows that for every negative charge there has to be a counter ion, so the magnesium is going to be next to the negative oxygen. There are no good leaving groups in my tetrahedral intermediate, so the oxygen picks up a proton from the acid at the end of the reaction, and I get, in this particular case, I get a secondary alcohol. Anytime you attack an aldehyde with a Grignard, you're going to make a secondary alcohol. If you attack formaldehyde, that's going to produce a primary alcohol. If you attack aldehyde, secondary alcohols. And if you attack a ketone, you're going to get a tertiary alcohol out of that reaction. Alright, let's do a couple of problems in here. Let's attack formaldehyde. Formaldehyde is your most simple aldehyde, and you can attack it with Grignards or organolithiums. So I'm going to use phenyl magnesium chloride. And again, the carbon that's attached to the magnesium, this is a nucleophilic carbon. So it's going to attack the carbonyl, form a tetrahedral intermediate. And the tetrahedral intermediate, I have two hydrogens attached to it, to the carbon. And I just attached a benzene ring to it. It doesn't have any good leaving groups. It has two hydrogens, terrible leaving groups, and a phenyl group. It just came in. Let's not kick it out. So when you quench the reaction, when you're working it up with water or maybe hydronium, the oxygen is going to pick up the hydrogen from the water, and that's going to give you your, in this case, primary alcohol. If you take a ketone, let's take 2-pentanone, and let's use an organolithium for variety. So we are going to use methyl lithium. So you add methyl lithium to it, and then you go ahead and you add water to the reaction. But the methyl is going to attack the carbonyl, form your tetrahedral intermediate. I just added a second methyl, so now I have two methyls. My oxygen is negative. No good leaving groups. Carbons are not leaving groups. So when I add the water, that's when the hydrogen picks up the hydrogen right there. The oxygen picks up the hydrogen. And this one right here is a tertiary alcohol. So whenever I attack a ketone, I'm going to add a third carbon group to the carbonyl, and I get a tertiary alcohol out of that reaction.